Good morning. So today we will study the multiplication of vectors. In earlier two videos we have studied how to perform the addition of the vectors and the subtraction of the vectors. The third mathematical operation that we can perform with the vectors is the multiplication. So let us see how to perform the multiplication of the vectors. Whenever we multiply a given vector by a certain scalar, the multiplication by a scalar is very simple. The resulting vector has the magnitude equal to the product of the magnitude of the given vector and the given scalar. And the direction of the resultant vector is found to be same as the direction of the given vector. The direction of this resultant vector is found to depend on whether the scalar with which we are multiplying the given vector is positive or negative. If the given scalar is positive, then the direction of the resultant vector is found to remain same as the original vector, given vector. And if the scalar is negative, then the direction of the resultant vector is found to be opposite to that of the given vector. Now, where do we come across such situation? Whenever we want to obtain the momentum, as we know that the momentum is expressed as the product of the mass of the body and its velocity. Here, mass is a scalar quantity and velocity is a vector quantity. So, the momentum that results by multiplying velocity by mass is again a vector quantity. And that is how we can multiply a vector with the help of a scalar easily. If we want to divide the given vector by a scalar, the division to a vector by a scalar is very simple. Again, we can multiply the given vector by the reciprocal of the given scalar, so that we shall get the division of the vector by a scalar. Now, as we know that since the vectors have both magnitude as well as direction, the vector multiplication, if we want to multiply the two vectors, if we want to take the multiplication of the two vectors, this multiplication of the two vectors cannot be performed by using the usual laws of algebra or usual rules of algebra, as we perform in case of scalar multiplication. For this purpose, there exist two distinct rules for or kinds of multiplication of the vectors, depending on whether the multiplication of the two vectors results into a scalar quantity or it results into a vector quantity. The first type of multiplication is called as scalar product or it is also called as dot product of the two vectors. In case if the result of multiplication of the two vectors results into a scalar quantity, it is called as scalar product or it is also called as dot product of two vectors. And the second type of multiplication is the vector product. Or it is also called as cross product. If the result of multiplication of the two vectors yields to be a vector quantity, this type of product is called as vector product or it is also called as cross product of two vectors. The scalar product of two vectors is denoted by A bar dot B bar and it is expressed as A B cos theta, where A and B are the magnitudes of the two given vectors and theta is the smaller angle between the two given vectors. Whereas the cross product of two vectors is represented as A bar cross B bar and is obtained as A B sin theta n cap, where n cap is the unit vector in the direction of A bar cross B bar. N cap is the unit vector in the direction of A bar cross B bar. If we take this kind of multiplication of the two vectors, it results into a scalar quantity, whereas if we take this type of multiplication of the two vectors, it results into a vector quantity. AB sin theta is the magnitude of A bar plus B bar and this n cap represents the direction of this vector A bar plus B bar. So in detail we shall discuss this cross product later on. Since the scalar product of the two vectors is represented as A bar dot B bar, so this type of product is called as the dot product, and the vector product of two vectors is denoted as A bar cross B bar, so it is called as cross product. So next we shall see both these types of products of the two vectors one by one. So let us first discuss the scalar product or the dot product of two vectors. The scalar product or the dot product of two vectors is expressed like this: A bar dot B bar equal to AB cos theta, and is defined as the product of the magnitudes of the two given vectors and the cosine of the smaller angle between them. So if we have the two vectors as say A bar and B bar, and this is the angle theta the smaller angle between the two given vectors, then the dot product of these two vectors is expressed like this: a bar dot b bar is equal to ab cos theta, where theta is found to lie between 0 and 180. Theta is found to lie between 0 and 180. That is the smaller angle between the two given vectors. The value of theta should lie between 0 and 180. This dot product always has certain characteristics. Characteristics of the dot product. The first characteristic of the dot product is that if two vectors are parallel, if the two vectors are parallel to each other, then the angle theta between them will be 0 degree, so that cosine of 0 degree is equal to 1, and if we substitute the value of cos theta as 1 here, the scalar product of the two vectors then will result as a into b. That is, if the two vectors are parallel to each other, then the dot product of two such vectors is equal to the product of the magnitudes of the two given vectors. So this is the first characteristic. Then the second characteristic of this dot product is that if the two vectors are identical, then and if in addition the two vectors are parallel to each other, identical means they are parallel to each other and they are equal, so that if a bar is equal to b bar, it means that the magnitudes of the two vectors are same as well as their directions are identical, so that the dot product of such two vectors works out to be equal to a square or is equal to b square, because since a bar is equal to b bar, the magnitude of a bar is same as that of b bar, so that the dot product a bar dot b bar, since is expressed as a into b, so it is a into a or b into b, so it works out to be equal to a square or b square. So that is the second characteristic of the dot product. Then the third characteristic of the dot product is if the two vectors are perpendicular. If the two vectors are perpendicular to each other, then the angle theta between the two vectors will be 90 degree, and if theta is equal to 90 degree, the value of cos 90 works out to be equal to 0. The value of cos 90 works out to be equal to 0. Therefore, the dot product of such two vectors which are perpendicular to each other works out to be equal to 0, because dot product is expressed as AB cos theta. So whatever the magnitudes of A and B, since the value of cos theta is 0, the product will be equal to 0. So if the two given vectors are mutually perpendicular to each other, then the scalar product or the dot product of such two vectors will be equal to 0. Or other way around, if we observe that the dot product of the two given vectors is equal to 0, then straight away we can conclude that the two given vectors are mutually perpendicular to each other. So this is the third characteristic. The fourth characteristic of the dot product is that if the two vectors are antiparallel, which means that theta is equal to 180 degree. And if theta is equal to 180 degree, the value of cos 180 degree is equal to -1. So that the dot product a bar dot b bar is equal to minus of a into b. If the two vectors are anti-parallel, the angle theta between the two vectors will be 180 degrees, so that the value of cos 180 is -1. So the dot product of such two vectors will be minus of a into b. Then from this second characteristic, what we observe is that since a bar dot b bar is equal to a square, since a bar dot b bar is equal to a square, so we can say that the dot product of the unit vectors I cap dot I cap is same as j cap dot j cap is same as k cap dot k cap, and as we know that the magnitudes of the unit vectors is unit, the dot product of self dot product of the unit vectors will be equal to 1. From this identity. And then from this third identity, if the two vectors are perpendicular to each other, the dot product of the two vectors works out to be equal to 0. So what we can conclude is that the dot product of the unit vectors I dot z or j dot k or k dot I will be equal to 0. So see, because these unit vectors I and j are mutually perpendicular to each other, j and k are once again perpendicular to each other, as well as k and I are again perpendicular to each other, so that the angle theta between them is always 90 degree, and hence the dot product of such mutually perpendicular unit vectors will be equal to 0. So these are certain identities of the dot product, or characteristics of the dot product. Then we will see how to express the dot product, scalar product of the two vectors in terms of the magnitudes of their components. Scalar product in terms of the components of the given vectors. As we know that the vectors rectangular components as I cap ax plus j cap ay plus b cap az in space, and the vector b1 can be expressed as I cap bx plus j cap by plus k cap bz. So these are the rectangular components of the given vectors e bar and b. Now, if we take the dot product of these two vectors, and if these vectors are expressed in terms of their rectangular components, let us see what will be the result. I cap ax plus j cap by plus k cap az dot I cap bx plus j cap by plus k cap bz. So this product can be expressed as I dot I into ax bx plus I dot j ax by plus I dot j ax bz plus j dot I ay dx plus j dot j ay by plus j dot k ay dz plus k dot I az bx plus k dot j az by plus k dot k az bz. So this is the multiplication of these two vectors in terms of their rectangular components. Now, from this product, what do we observe is that the dot product of unit vectors I dot I is 1, j dot j is 1, and k dot k is 1. The dot products of the remaining vectors, unit vectors, that is I dot j, I dot k, j dot I, j dot k dot I, and k dot j, all are equal to 0, because here I and j are mutually perpendicular to each other, I and k are again mutually perpendicular to each other, j and I are perpendicular, j and k are perpendicular, k and I are perpendicular, k and j are again perpendicular, so that the dot product of these unit vectors which are perpendicular to each other, since is equal to 0, so all these terms will vanish, and the terms that will remain are so a1 dot b1 will be equal to I dot I ax bx plus j dot j ay by plus k dot k az bz. And since the self dot product of the unit vectors is equal to 1, so we can express a bar dot b bar is equal to ax bx plus AY BY plus AZ. So this is how we can express the dot product of the two vectors in terms of their rectangular components. So we can express the dot product of the two vectors in terms of their rectangular components. So A bar dot B bar is equal to AX BX plus AY BY plus AZ AZ. So that is what we can express the dot product of the two given vectors in terms of their rectangular components. When taking the dot product of the two vectors in terms of their rectangular components, certain laws are obeyed or are valid. So let us see which laws are valid when we take the dot product or the scalar product of two vectors. The first is the dot product of two vectors obeys commutative law of multiplication. Obeys the commutative law of multiplication. What does it mean? It means that the dot product A bar dot B bar is same as the dot product B bar dot A bar. Even if we change the order of the two vectors in the product remains unchanged. So this is called as commutative law of multiplication. We have said that A bar dot B bar is expressed as AX BX plus AY BY plus AZ AZ. And if we evaluate the dot product B bar dot A bar, it will be equal to BX AX plus BY AY plus BZ AZ, or this again can be expressed as AX BX plus AY BY plus AZ BZ, and this is AY what AY. So here we have changed the order of the magnitudes of the two vectors so that we get this expression. And this expression is nothing but the expression for A bar dot B bar. So what we have to is that B bar dot A bar is nothing but equal to A bar dot B bar. Hence, that is what we observe from this first law, commutative law of multiplication. The second law that is obeyed is the dot product obeys the distributive law of multiplication. The dot product of the scalar product obeys distributive. Of multiplication. That is, if we want to evaluate the dot product of the vector A bar with the sum of the vectors B bar and C bar, how to evaluate this dot product? So this dot product can as well be expressed as A bar dot B bar plus A bar dot C. So this dot product is distributed over the two terms in this parenthesis. So that first we can evaluate the dot product of A bar and B bar, then evaluate the dot product of A bar and C bar, and then get the addition. So this this is called the distributive law of multiplication. And the third law that is proved by this scalar product or the dot product of the two vectors is when we multiply the dot product by a scalar n. Suppose we want to multiply the dot product of two vectors, say a bar and b bar, by this scalar n. How to evaluate this product? This product can be evaluated first by multiplying the vector a bar by the given scalar n and then take the dot product with the vector b bar. Or we can evaluate it as first take the multiplication of the vector b bar by the given scalar and then take the dot product of a bar and b bar. Or as well we can evaluate first the dot product of the two different vectors a bar and b bar and then multiply it by the scalar n. So all these products results in the same result. So these are the laws that are being obeyed while taking the dot product of the two vectors. So let us see few examples of this dot product or scalar product of the two vectors. In what situation the result of multiplication of the two vectors results into a scalar quantity? In what situations the multiplication of the two vectors results into a scalar quantity? The first example is the work done. As we know that the work done W is expressed as the dot product of the force and displacement, where force is a scalar vector, displacement is again a vector, and if we take the product of force and displacement, that is the product of two vectors, it results into a scalar quantity called as the work done or work. This is the mechanical. So this is the first example of the scalar quantity. Then second example is the power. The power is represented as P. The mechanical power is expressed as P is equal to the dot product of the force and velocity. Here force is a vector quantity, velocity is again a vector quantity, but if we take the dot product of these two vectors, it results into a scalar quantity, and that is called the power, mechanical power. The third example is the magnetic flux. Denoted by pi, and this magnetic flux form is expressed as the dot product of B bar and B bar, where B bar is the magnetic induction, it is a vector quantity, A bar is the area vector, so that the dot product of these two vectors results into a scalar quantity called magnetic flux, and this magnetic flux gives the total number of lines of force passing through a given area A perpendicular to it. The magnetic flux passing normally through the given area, and that is called as the magnetic flux. So, if we have this area A and the magnetic induction is calculated like this. This is magnetic induction B. If we represent this area A by the vector A bar, this is the area vector A bar, then the flux due to this magnetic field passing normally through this area, it is like this. This is the flux phi. This flux phi passing normally through this area A is obtained by using this dot of B bar and A bar. So this is B A cos theta. So this is B A cos theta, where A cos theta is this is equal to A into B cos theta, where B cos theta is the component of the magnetic field in the direction perpendicular to the area. So it is B cos theta. So that is how, or in these situations, we observe that the product of the two vectors results into a scalar. And there are many more situations where we come across this kind of product, scalar product of the two vectors. This scalar product of the two vectors is nothing but the product of the magnitude of one vector and the component of the second vector in the direction of the first vector, that is A B cos theta. So that can be explained like this. This scalar product is nothing but the product of the magnitude of one vector and the projection of the other vector in the direction of the first vector. Suppose we have this vector A bar, this is the vector A bar, and we have this vector B bar. The angle between the two vectors is theta. So, if we draw the projection from the end point of the vector B bar in the direction or on the direction of A bar, then this is nothing but the component of B bar in the direction of vector A bar, and this is nothing but equal to B cos theta. So, if we take the product of the magnitude of A bar, so A bar dot B bar is nothing but equal to A B cos theta. So, this is equal to A into bracket B cos theta. So, this B cos theta here is nothing but the component of B bar in the direction of A bar. So, it is expressed as A into B cos theta, where A is the magnitude of B bar and B cos theta is the magnitude of the component of B bar in the direction of A bar. Or else, this product as well can be expressed as this. So, if we produce this vector B bar in this direction, and if we draw a normal from the end point of vector A bar on the vector B bar, this will be the component of A bar in the direction of B bar. So, this will be A cos theta. So, we can as well express this product as, instead of writing A into B cos theta, we can as well express it as B into A cos theta. So, this is nothing but equal to B is magnitude of B bar, and A cos theta is the component of A bar in the direction of B bar. So we can express this dot product as, in general, magnitude of first vector into the component of second vector in the direction of first vector. So the dot product of two vectors is nothing but equal to the magnitude of the first vector into the component of second vector in the direction of the first vector, or vice versa. That is the magnitude of the second vector into the component of first vector in the direction of second vector. So the dot product of two vectors can be expressed like this, and if it is so, then we can say that A bar dot B bar is same as B bar dot A bar. So that is about the scalar product or the dot product of two vectors. Next we want to discuss is the vector product or the cross product of two vectors. That will continue in the next video. Thank you.